Okay. So now, the question that we tend to ask ourselves is, how do we know that this equation is correct or wrong? Right? How do we know? Anyone? How do we know that if this equation is right or not? I'm going to look at the chat. Is anyone typing? How do we know that the expression is correct or not? Anyone? You can speak up. So just to make it, let you, or we were to recall. So under constant thickness, okay, so this is constant thickness, right? And if this is our geometric centroid, right? And this is our shear, we tend to get a distribution looking like this. So this is under constant thickness. So we have formulated an equation that has constant thickness. So the distance furthest away from the centroid, right? So i.e. when t is equal to 0.035, this equation over here must be equal to what? 0. So if you put on 0.035 squared, you can do this at home, times by 7.741 power 9, and then minus by 9.483 power 6. Yeah, I got 275 Pascal, which is as good as equal to what? Equal to 0. Okay, so this is how you check. Okay, right. So this is from the limits from 0.015 to 0.035, right? So this is where you see, right, the piecewise equation are dependent on the what? On the thickness, okay? So the next one we're going to do, we're going to work on to the next thickness now, or the next section. So the next section, right? So again, this is the position of our centroid, right? So now we have dealt with this section already. So this section is done. Okay, this section is done. So we've dealt with this section already. So the next section we're going to look at is the section up to the where? Up to the geometric centroid, or up to the datum. Why we start at the datum is because the first moment of area cannot cross the what? Cannot cross the datum. Okay, so we stop at the datum. So from here, we know our limit. We know at this point, this is equal to 0.015. Let me write clearer. We know that this is equal to 0.015. So next, our next set of limits is now the thickness is equal to 0.04. Why 0.04? You have 20 over here, you have 20 over there. Add together is 0.04 meters. So now the limits change, right? From 0 y up to a y of 0.015 meters. Based on y, this is our transformation, y and z, and we have our rotation about x. Okay. So from here, again, we know that the formula we're going to use. We know Vy, Izz is constant, Qz as a function of y is changing, and we know our thickness, right? So now we have to find Qz as a function of y. So for this case, we have to do Qz for the flange. So the flange will be constant, okay? The flange is constant because if you look at this limit is within this range over here, okay, where I'm highlighting my arrow in yellow, okay, within that range. So within that range, you still have to calculate the first moment of area of the flange, and now it's constant. It's no more a variable. And then next, we do a plus Qz, then it is for the web, and it's going to be a function of y now. Okay, so this will be the width. So as usual, this is our width, and this over here is our depth, right? So the width is 0.16 for the flange. The full depth is 0.02, and the y bar is equal to 0.035 minus by 0.02 divided by 2. And why that is the case is because we know that you have, this is the centroid for the pink section, and the distance from here to here is 0.02 divided by 2. Okay, so we want to find the y bar for this distance over here, okay, for the flange. Next, we are going to do the web, right? So we have the width, okay. So twice is the left and right. Thickness is equal to 0.02. And then the limits again is very easy. The maximum distance in that range minus y multiplied by 0.015 plus by y and then multiply by half. Okay. So from here, this will be equal to 0.0 minus y 0.02 divided by 2 times by 0.2 times by 0.16 is equal to 80 times 10 to the power minus 6 plus by 0.015 squared times by 0.015 squared times by 0.5 times by 2 times 0.02 is equal to 4.5. And then minus by 0.02 y squared. So this will give us our 80 power minus 6 plus by 4.5 power minus 6. So it's 84.5 times by 10 to the power minus 6. And then we minus by 0.02 y squared. Okay. So from here, we can calculate shear xy as a function of y. So this will be equal to v. We know it's 90 times 10 to the power 3. Divide by our y izz is 5.813 times 10 to the power minus 6. Then we include 84.5 times 10 to the power minus 6 minus by 0.02 y squared. And then we divide the whole thing twice of 0.02. We all is equal to 0.04. Okay. So from here, this will be equal to 90.3. That's right, 84.5 power minus 6 is equal to 30. Hold on, I'm having a 90 power 3 times 84.5 power minus 6 divided by 5.813 power minus 6 equal to 32.7. Hold on, I keep on pressing my calculator on 84.5. So 80 power minus 6 plus by 4.5 power minus 6 is 84.5. Yep. So 90 power 3 times by 84.5 power minus 60 by 5.813 power minus 60 by 2 divided by 0.02. So I get 32.706 or 32.707 times 10 to the power 6 minus by 7.741 times 10 to the power 9 y squared. Okay, so this is from the limits from 0y to 0.015. Now, the other question is, how do we know that this is right? Okay, so the only way to check, okay, to check whether this is right or wrong, okay, so to check, to check is to determine shear xy as a function of y, and now we switch the limits from 0 y to 0.065 millimeters or 0.065 meters by considering the bottom section, right? So remember we did this example by if we look from the top or from the bottom, the first moment of area has to be the same. Okay, so that's what I'm going to do now. Okay, so we're going to now do this by considering the bottom. Yeah. So now if we were to consider the bottom section, the answer has to be the same. If the answer is wrong, fundamentally there's something wrong with what we have just derived. Okay. So now, so we call this the top section. Down here is the bottom section. So we know that this is 35 millimeters. So we're going to consider the bottom section, where thickness is equal to what? Thickness is equal to 0.04 meters. And the limits is again 0 to y, and then we are going to go down by 0.065 meters. Okay, so this is 0, and this position over here is your 65 millimeters. Okay, so now the formula is so much easier now, right? So Q, first moment of area, about the z-axis as a function of y. The width will be twice, right? 0.02. The y bar is equal to 0.065 minus by y, and then we have 0.065 plus by y multiplied by half. Oops. Yep. Sorry. Multiplied by half. So our first moment of area, either we take from the bottom or the top, should be the same. So if I do this now, so this is good. 0.065 times by 0.065 times 0.5 times by 2 times by, wait, 2 times by 0.02 times. Okay. So it's equal to 84.5. Right? And then we have minus 0.02 y squared. So if you look at this expression over here, right, by considering the bottom, and if we consider the top, the first moment of area is exactly the same, right? So whether you derive from the top or you derive from the bottom, the answer will be and shall be always be the what? Always be the same. Okay? So we have done this briefly before, I think in one of the examples last week. Okay, we calculate from the top and bottom. The first moment of area is the same, but down here is a function of y. Okay. So now how to use these equations? Okay, so let's say now if we're going to find the shear stress at point A. Okay. So the shear stress at point A, the equation that we are going to use, right? The equation, so we are going to use that y is equal to what? Y is equal to 0.055 meters. Okay, so the equation that we are going to use will be shear xy as a function of y. So we're going to use this expression over here. Okay, we're going to use 32.707 times 10 to the power 6 minus by 7.741 times 10 to the power 9